And you sum it up. That's unfortunate, you only need one variable. That center square didn't make it too hard. And you basically get another exponential generating function. Right, so we've taken care of H, horizontal, vertical, 180. Let's do diagonal reflection. Have I taken care of that? I know, I hate when people ask me these types of things. Let me erase something out of the board. Let me do diagonal. All right, let's go elsewhere.
So you first had this summation formula, and then you got the generating function?
Yes.
Oh, but you have to do it directly. Look at the connected components and count the connected components. Do you think you might be able to do it this way?
You could, yeah. I've used the same game. I just got so used to thinking about building it and then just doing the sums. I mean, yeah, there might be a more efficient way to do this.
Yeah,
Yeah,
it's beautiful formula. So
yeah, and the nice thing is, right, you close them all. I mean, they are beautiful. Yeah, they have nice close. But all right, just to give you a hint about, let me draw 3 by 3 square. Okay, and here's our diagonal reflection. This is what's fixed. So we got to work around the fixed row. Did we ever work a fixed kind of row? Here's the key. Did we ever do anything where we had to work around a fixed row before?
Yes.
Yeah, what one?
We do the odd case.
Yeah, and that's exactly how you could do it. I didn't realize this. I had even another way of counting this, and I noticed that when I did the final count, these two worked out the same. Yeah, basically here is the top half you have to fill in, and then you do this. It's exactly counting the So those coefficients in that odd generating function for Hn actually will give you the diagonal. And so basically what it comes, so that's why I only recorded this way. The V goes with my original X, if you can remember that, and the T goes with Y. That's why it's two-dimensional. So if you were really efficient, you've already done diagonal. So all we have to do talk about in our last couple of minutes is 90, and then we're on the open question. Now, I actually did this a whole other way, and then that guy saw that it was exactly one and the same. I said, oh, if I were really clever, I would have noticed this to begin with. Okay. So now let's look at 90. Now we come to, when you do 90, now you have to do quarters. All right, and so basically, there's a lot of pictures here. I'll just wave my hands. You basically, when you do 90 degrees, you have a square. Then once again, we're going to have to split this into evens and odds because I need to worry about whether something's fixed. The center square, when you rotate, you have to worry about whether this central thing is fixed. So basically, you take this you basically look at a quadrant. You arbitrarily fill it, and then you have to make some analysis about how the rotation takes those letters. Okay? Now I'm going to start even, because even's always the easier case. If you want to figure out what the symmetry is doing, if it's an even square, there's nothing fixed, and we're happy. All right. Now I called the figure 11 singletons, because what happens is that this letter appears in the, I always fill the upper left quadrant. And when in its image under a 4 cycle, because it's a rotation, you have to have 4 letters in each quadrant, well, that image never reappears. Its image in that cycle never occurs in the quadrant again. So there's 3 possibilities. It could rotate to itself, it could go A, B, A, B, or it could rotate to 4 new letters. Well, now we get fancier. So we have 3 other types of things we have to do. 3 other types of 4 cycles. Well, this is the 4 cycle where only 1 letter appears in the upper left or first quadrant. Here is 4 cycles where 3 of the letters must appear in the upper left quadrant. There's 6 images. Okay. You don't have to memorize these. These are hard to memorize, but you can just experiment with drawing a lot of pictures and you'll convince yourself there's 6. Here we have 4 cycles. Only when 2 of the letters appear in the upper left quadrant, and then the other 2 images don't. Notice I don't have A to X I don't have A, Y, B, X. That's considered the same as A, X, B, Y. You see, so that's why. And then finally, what would be left over? If I had 1 letter, 3 letters, 2 letters, what could I have left? Well, 4 letters, and guess what? That's the next picture. Okay. Okay, so that's what I'm going to do. And so basically now what you do is you construct your little summation. It's not nested. Look at summation. Fill your upper left quadrant. You count how many singletons. You count how many 3 pairs occur in the upper left quadrant, how many 4 pairs, and how many 2 pairs. You do this game. And you get, once you put in the variables, you get this nice exponential generating function. All right, so we only have one other thing. We have to look at odd, square, 90 degree, and it's almost the same game. However, you have a central square, and so now you have to subdivide into these little rectangles. So part of the game with this is always finding out what's considered the basic thing you want to do with your symmetry, and then work around what's fixed. And it's almost the same thing. Basically, you have your types of 4 cycles, and you have to determine what could go in the middle square. And the types of letters that could go in the middle square are those, there's only something that never appears anywhere, brand new, or that first singleton, that's it. And that's your thing. Okay. So once you put all of these together, I can get I'd have a very good lower bound. Now there's a way to tweak these. And what you're going to notice, if you go back to, since I have a little bit of time, let's go back to this picture. Notice what happens. You never can, let's look at this thing. Look at the orange component, the thing passed around. Can I ever have 2 outward pointing back, 2 outward? No. So that's the first thing. So we can now put these circles in, and it's basically taking, I'm not going to get into too much, it's basically taking your first Stirling number and multiplying it by 2 binomial coefficients. And so you can do this whole symmetry thing, but carefully keeping track of the arrows, or the circles. And that will give you the upper bound for these. Okay? I have all them. I don't want, they get a little messier because you have more cases to look at. I mean, but because there's arrows in it. And then you can always check that your answers were correct by basically taking out some of the extra variables and see if you got what you got with an arrow case, or an circle case. All right. And one of the questions somebody asked me with these generated functions, do I know they ask methodologies? Not really. But what I can say is as your squares get more and more rows and columns, your final answer is going to be closer and closer to the upper bound. It's a much better estimate. So now here's the open question, which has been bothering me for many years. I only have an upper and lower bound. I'd like to get an exact count. So what do I need to get an exact count? Okay. Now, you need an additional adjacency condition. All right, so let me give you this. Suppose I have a 2 by 2 square, and I want to say its transition matrix, preferred face state looks like this. I need to build it out. Can I build that? You have some cubes. Can you build? Can you even build a 2 by 2 by 2?
Should it become kind of cross?
You can't cross them.
Yeah.
You can't. I claim this can never be built. I've got to rule these out. My original count has never ruled them out. I just throw any arrangement of letters in, which is a build-up. That would be such a proper arrangement. So when I do this...
Oh, so you give upper bounds.
I have upper and lower.
And subset.
Yeah, I have it.
And a subset.
Yes, I have upper and lower bounds. The upper bound, as the n gets bigger and bigger, the upper bound is going to be more and more accurate because what I'm going to describe is what I don't have. I have to rule out some adjacency condition. This is where I'm stuck. But now here's the key. This can be built.